We're going to find solutions of a system of differential equations in the form x prime equals ax, where we end up with two complex solutions. We're still going to be finding the eigenvalues, then we're going to find a corresponding eigenvector, and then we'll build the solution. The vector x prime is equal to the matrix -1, 2, -1, -3 times the x vector. We're going to first again find the eigenvalues. As always, we take the determinant of a minus ri and set it equal to 0. Here's what it works out to be, and after I multiply everything out and combine like terms, I get this. Now this is infactorable, so I'll have to use the quadratic formula. Again, I'm not going to bother showing you the quadratic formula. I'm confident you can do so. But when we do, we get the following answer. Or I should say answers, because in this case we get a plus and a minus of the imaginary number. Again, our two solutions are complex conjugates of each other. What we're going to do is we're always going to take the positive imaginary value. That is, I'm always going to take the form r equals alpha plus beta I. So in this case, the eigenvalue I'm going to use is -2 plus I. That means alpha is -2 and beta is equal to 1. Using this one eigenvalue, I'm going to find a single eigenvector. So this is again a little different than when we did two real solutions, or even when we did one repeated real solution. So let's go ahead and find that eigenvector. We use the same formula as we've done before, and we get this. Now I'll simplify things, and I get to this. I must admit, it doesn't look like the second row is in fact linearly dependent with the first row, but it actually is. If we multiply things out and we remember that I squared is equal to -1, the first row and the second row are in fact dependent. So again, I'm only going to use my first row in order to find my eigenvector. I'll rewrite u vector as u1, u2, and I get it in this form. Now to be honest, I'm going to go ahead and multiply both sides by -1 because I'm not a big fan of having extra negative signs, but you don't have to. Again, we're going to remember that we always swap our coefficients, and then we'll see that the eigenvector is simply this. Now, we always have had two different eigenvectors. So here I have a single eigenvector. Well, what I'm going to do now is I'm going to split this eigenvector into the real portion and the imaginary portion. And I do so like this. I'm going to call the real portion of the eigenvector as A, and the imaginary portion as b. Notice that b doesn't have an I in it. It's just what is ever multiplied by the I. And when I do that, I can go ahead and use the formula that you'll be given on the exam. And this is what's going to be given to you on the exam. I have a hard time remembering if it's the cosine and then the sine, and if it's then the sine and then the cosine, and where the plus or minus goes. I don't want to get caught up in those kind of errors on the exam. So as long as you know how to use this, we'll be fine. So, given this, we can find our final solution. Recalling that our eigenvalue r was r is equal to -2 plus I. That means alpha is -2 and beta is I. We come up with this for our final solution. We can write it in another way. We could combine these vectors, and we can write it as such. Make sure you understand how to go back and forth between these two different forms.